Limits of functions and limit laws. The objective of this lesson is to evaluate a limit of a function as it approaches some value x. And so we're going to start by considering this function below. We have the function f of x equals x cubed minus 1 over x minus 1, and we want to know the behavior of this function near x equals 1. Because, of course, we can see that if x equals 1, we have a 0 in the denominator, and therefore the function is undefined. So we could use some normal curve sketching techniques, except at x equals 1, where the graph is undefined. So what we're going to do is we're going to construct a table of values to try to help us better understand what happens to the graph of the function as x gets closer to that value where it is undefined. So I've gone ahead and made a table of values here, and you can see that if my point in question where the function is undefined here is 1, and I'm getting closer and closer to 1, so I have 0.75, my function value is 2.313. 0.9, my function value is 2.710. 0.99, 2.970. 0.999, I get 2.977. So I'm fairly close to 1 here, but less than it. And then I kind of have the same thing going on here as I get closer and closer to 1 on the right-hand side, but stay greater than that. So we can sort of see from these two values, when we're really close to 1 on the left-hand side at 2.997, and when we're really close to 1 on the right-hand side at 3.003, we can kind of guess that probably the function, even though it is undefined at x equals 1, the function value maybe approaches the value 3 as x approaches 1. Okay? And it turns out that if we do some algebraic simplification of the function, we can get a clue as well. So here I can factor the difference of cubes, as I have in the numerator here, and then I can cancel out those factors of x minus 1. So basically these two functions are equal as long as x is not equal to 1. And so if I were to sketch the graph of this function, it is a parabola. And so when I look at it, I'm going to have a parabola with a hole in the graph because it's not defined at x equals 1. Okay? And so we can see that here if we look at, okay. So we can see then that in this graph, this is the graph of a parabola, and there's a hole in the graph at x equals 1. So at the point 1,3, there's a hole. But we can see that as we approach that point on the function, if you watch the y values here, they're changing and they're getting closer and closer to 3. And then if we go above the function, they're also changing and getting closer and closer to the value 3. Sorry for my unsteady hand here. But you can sort of see what's going on. So we start here at 2.44. We increase as we get to 3. And then we see our y values also approaching 3 from this side. All right, so this idea actually gives us our informal definition of a limit. So even though the original function is undefined at x equals 1, we can see that the function values approach 3 as x gets closer to 1 from both directions. So therefore we can say the limit as x approaches 1 of the function is equal to 3. Okay, so that's our informal definition of limit. So in general, if f of x becomes arbitrarily close to some number L, as x approaches a value c from either side, then L is said to be the limit of f of x as x approaches c. And we use this notation, limit as x approaches c of f of x is equal to L. Okay, so that's the notation for our limit. All right, so the limit does not depend on the value of the function at c or whether or not even the function is defined at c. So if we look at the graphs below, the first one is x squared minus 1 over x minus 1, and you see we basically have a line with a hole in the graph up here at x equals 1. But if we approach 1 from either side, we can see that our function values are approaching a particular number here, which happens to be 2. And so that means that we could say here that the limit as x approaches 1 of this function is equal to 2. Okay? Similarly here, even though the function is a piecewise defined function, so the function is defined at 1, so we have that f of 1 is actually equal to 1. But still, as we're approaching 1 on the function, as x is approaching 1 on the function values are still approaching this value too. Okay? So this would still mean that the limit as x approaches 1 of the function is equal to 2. So here we have the function, the first one we have the function is undefined at x equals 1. The second one, it's actually defined, but the limit is not the same as the value of the function. Okay? And in the third case here of h of x, we know that, actually I should call this g, shouldn't I? Because that's what we called it down here. So for h of x, if we look at h of 1 in this case is 1 plus 1, which is 2. And as we approach 1, the function values are also approaching 2. So we have that the limit as x approaches 2 of h of x is equal to 2. So in all three pictures, the limit is 2 because it depends on what the function is doing as x is approaching 1. And so even though the first one, the function is undefined, but the limit exists, it equals 2. The second one, the function is defined and the limit exists, but those two things are not equal. And in the third one, the function is defined and the limit exists, and those two things are equal. So basically, the point is the limit is always the same, and it doesn't matter how the function is defined at the point. Okay? So finding limits graphically. So this says find the indicated limit. So let x equal 1 for x not equal to 3, and negative 1 when x is equal to 3. So just a real quick sketch of the graph of this function. It's piecewise defined, and when we have x equal to 3 here, the function value is negative 1. Okay, so that's from this piece of the function. But when x is any other value not equal to 3, the function value is 1. So the function value is 1 everywhere except at this point. So that means it's going to be 1 going all the way to negative infinity and 1 going all the way to positive infinity. Okay? And so now the question is to find the limit as x approaches 3 of this function. And so we can see by the graph that as x is approaching 3 along this function from both directions, the y value here that it's approaching is equal to 1. This is this value over here. Okay, so the limit graphically we can see is equal to 1. Okay, so this actually gives rise to a little theorem here, because basically this was a constant function except for the redefinition here at the point x equals 3. All right, so we have actually two things that help us find the limits. And one is that the limit of the identity function, so that is the function f of x equals x, then for any constant c, the limit as x approaches c of f of x is simply going to be c. So you can see that by looking at the graph here. As we come along the graph, as x is getting closer to c on the x-axis, y is also getting closer to c along the y-axis. So that is the limit of this is equal, the limit of as x approaches c of x is equal to c. And furthermore, from our picture above, or from this picture here, we can see that the limit of a constant function is just going to equal that constant, because again, as we're approaching any value c along this horizontal line, our function values are always approaching the value k. So these are two very important limits. The limit as x approaches c of x is equal to c, and the limit as x approaches c of a constant function k is equal to the constant. So now these two should be fairly easy to do. We have the identity function right here. So without even drawing a graph, since it's the identity function, according to what we just showed, the limit as x approaches negative 3 of x should simply be negative 3. And the limit as x approaches negative 3 of the constant function 7 should just be that constant, which is 7. All right, so it is possible that a limit does not exist. So here are some ways that limits cannot exist. This particular function in the first picture, we have, it's called the unit step function. It's basically when x is less than 0, it's at 0, and when x is greater than 0, it's up here at 1. Okay? And so this would be the case, this function u, if we took the limit as x approaches 0 of this function, it actually does not exist, which we'll abbreviate dne, because as I'm approaching from the left-hand side, my y values are approaching 0, but as I'm approaching from the right-hand side, my y values are approaching 1. Okay? And so in order for the limit to exist, it has to be from both sides approaching the same value. All right, so function g here is basically the hyperbola 1 over x, y equals 1 over x, as long as x is not equal to 0, but it's redefined to be 0 at 0. So we see the graph of this function here. So now this one also, if we took the limit as x approaches 0 of g of x, this limit also does not exist, because as we're approaching 0 from the left, we're actually going down to negative infinity here, okay? And from the right, as we're approaching 0, we're actually going up to positive infinity here. Okay, so again, the left and the right, because remember, the limit has nothing to do with how the function is defined. It has to do with what it's approaching as we approach the x value 0. And so in this case, one side and the other side, again, are not approaching the same value. One is increasing without bound and one is decreasing without bound. And actually, even if both sides were doing this, going, towards positive infinity, we would still say that limit does not exist, because they're not approaching a set value. They're going up to positive infinity forever. And then another case where a limit does not exist is if you have some wild oscillations going on. So this particular graph, as you go along it, on the bottom piece of it here, where you have x greater than 0, As the closer it gets to 0, the more it just jumps up and down, up and down, up and down. And closer to 0, it's always bouncing up and down between this -1 and 1. And it's never settling on any number. So we would also say here that the limit as x approaches 0 of f of x does not exist. So this is kind of the behavior of how limits look when they don't exist. So if you approach from the left and the right and you get two different values, if you approach and you increase or decrease without bound, or if you have some wild oscillations happening near the particular value we're approaching. So here's actually another case where the limit does not exist. And the reason the limit does not exist as x approaches 0 of the square root of x is because there are no values to the left of 0 in the domain of the function. So in order for the limit to exist, as x approaches 0, we have to be able to come on the function from the left, from the right, and we also have to be able to come on the function from the left, but there's nothing over here to come on. So since the domain to the left of the point in question is not does not include any points, that would mean that this limit does not exist. Okay? Because we have to be able to approach it from both sides. All right. So to summarize, behaviors of limits that do not exist. F of x approaches a different number from the right of c than from the left of c. So that was one case. F increases or decreases without bound as x approaches c, or we have a vertical asymptote in that case. Or F oscillates between two fixed values, like the third picture we saw above. And finally, the domain of F does not contain points on one or the other side of our point in question. Okay? All right, so this one says, find the indicated limit if it exists. So we want to know if this limit exists. So we're going to take a look at this function. So if we look at the function in question here, f of x is equal to the absolute value of x minus 1 over x minus 1. Okay? Remember the definition of absolute value. In general, the absolute value of x is defined to be x if x is greater than or equal to 0, but it's actually the opposite of x if x is less than 0. Okay? So in this case, because it's x minus 1 is 0 at 1, so we would say that the absolute value of x minus 1 is equal to x minus 1 if x is greater than or equal to 1, but it's equal to the negative of this if x is less than 1. Okay, just using the exact definition of absolute value, but the only difference is the 0 is when x is equal to 1, not when x is equal to 0. All right, so that means that we can redefine this function when x is greater than or equal to 1, then we're basically just going to have x minus 1 over x minus 1, which is 1. Okay, because the absolute value of x minus 1 is x minus 1 in that case. But when x is less than 1, then the function is going to be negative x plus 1 over x minus 1, which is the negative of x minus 1 over x minus 1, which is actually negative 1. Okay? And so that means if we are approaching from numbers bigger than 1, so if we're approaching from the right, our y values are approaching positive 1. But if we're approaching from the left, our y values are approaching negative 1. And so therefore this limit does not exist. Okay? And the reason it does not exist is because as x approaches 1 from the right, the function approaches 1, but as x approaches 1 from the left, the function approaches -1. Okay? And so the limit does not exist because they have to approach the same value from both sides. All right, some basic rules for limits to help us simplify functions when finding limits. And these are actually listed in the theorem below. So basically this just says for the sum rule, if we take the limit of the sum of two functions, it's going to be the sum of their limits. Okay, and we're assuming that L, M, C, and K are actually real numbers. Okay? The limit of the difference of two functions is going to be the difference of their limits. If I have a constant multiple times a function, then the constant multiple times the limit of that function. So in other words, the constants actually can pull outside of the limit. For the product rule, if you take the limit of the product of two functions, you're going to get the product of the limit. Now be careful, because this is only the case if L and M are real numbers. If L and M are not real numbers, then we have a problem there. For the quotient rule, again, if we have limit of the quotient, it's going to be the quotient of the limits, as long as, of course, our denominator is not 0. For the power rule, if I'm taking a function raised to a power, then it's going to be the limit raised to the same power. And the same thing for radicals, as long as n is a positive integer. And of course, if n is even, we have to assume that f of x is non-negative, or that nth root does not exist. So using the properties of limits. So remember, the two things that we have right now are actually that the limit as x approaches c of a constant function is equal to the constant, and the limit as x approaches c of the identity function is equal to c. So we can use that to find limits of, for example, this polynomial function, and use the properties that we just discussed. So this would actually be, first of all, using the sum and difference rules, this would be the limit as x approaches 2 of x cubed, plus the limit as x approaches 2 of 4x squared, minus the limit as x approaches 2 of 3. So this is by the sum and difference rules. Okay? And so then this one, we can think of it as the limit as x approaches 2 of x times x times x, plus the constant multiple rule tells us that this 4 can come out, and we'd have the limit as x approaches 2 of x times x. Okay, so I'm just going to write right here, this is constant multiple rule. Okay, and then minus, well, the limit of the constant we know is just equal to the constant. Okay, all right, so now basically on these two, we can use the product rule. So the product rule says the limit of the product is equal to, this is going to be a lot of writing here, but it's the product of the limits. So here we're going to have limit as x approaches 2 of x times limit as x approaches 2 of x. So that's this term up here. and then minus the 3. Okay? And so, of course, this is our product rule. Okay? And so now the limit as x approaches 2 of x is 2. So this is just going to be 2 times 2 times 2. Plus, over here, we're going to have 4 times 2 times 2. And then, of course, the minus 3. So this is just evaluating the limit. Okay? So now, of course, this is just equal to 8 plus 16 minus 3, which is 21. Okay? And so this just illustrates how we're using all of those different rules. But we can kind of take a shortcut here, you know, because notice what we got is we got 8, which is 2 times 2 times 2, which is the same as 2 cubed. Okay, so if I put the 2 in here, I'm going to get a 2 cubed. And then here we got 16, which is 4 times 2 times 2, which is the same as 4 times 2 squared. And then the minus 3, which is here. So basically, all those limit rules just gave us a nice, easy way to find the limit of a polynomial function. So we could actually simply go the limit as x approaches 2 of x cubed plus 4x squared minus 3 should simply equal 2 cubed plus 4 times 2 squared minus 3, which is 8 plus 16 minus 3, or 21. Okay, which is, of course, a lot less work. But I wanted to show you how all of those different limit laws apply to come up with that if we have a polynomial function and we're taking the limit, we can simply evaluate it by plugging in the number. All right, and so basically these two, numerator and denominator, are polynomials, so we can evaluate them by plugging in. But also, we also have the rule that the limit of the quotient is equal to the quotient of the limits. So this should actually be okay. This should actually be this. So limit of the quotient is equal to the quotient of the limits, and that's by the quotient rule. Okay? And so now, since these are polynomials, by what we just discussed above, we can evaluate those by plugging in. So we can say this is just going to be negative 1 to the 4th minus negative 1 squared minus 1. And in the denominator, the same thing. Negative 1 squared plus 5. And of course, the quotient rule applies as long as our denominator is not equal to 0. And we're okay here because our denominator is not equal to 0. And so this is going to be 1 minus 1 minus 1 over 1 plus 5, which is negative 1/6. Okay? All right. Now again, here we can use the rational exponent rule, or the root rule. So this is actually going to equal the square root of the limit as x approaches negative 2 of 4x squared plus 3. And that is this rule here, the root rule. Okay? And so this is going to equal the square root. So let me write root rule here. So this is going to equal the square root of, now we have a polynomial, so just plug it in, 4 times negative 2 squared plus 3, which is equal to the square root of 4 times 4 plus 3. 16 plus 3 is 19. So the answer is, the limit is the square root of 19. So what I just showed in all the previous examples boils down to this. If we want to take the limit of a polynomial function, then we can just evaluate the polynomial function at c. So in other words, the limit as x approaches c of p of x, where p of x is a polynomial, is simply equal to p of c. And similarly, if we want to take the limit of a rational function, as long as our denominator is not equal to 0, that's important right there, is I can also just evaluate the rational function at c. Okay, so I just showed you that with those examples above. So that means in this case, we can just go, well, this limit is just going to equal negative 3 cubed plus 4 times negative 3 squared minus 3, because we're looking at the limit as x approaches negative 3. So this is negative 27 plus 4 times 9 minus 3. So that's negative 27 plus 36. So negative 27 and 36 leaves 9 minus 3 is 6. And here, as long as our denominator is not equal to 0, so if I plug the 2 in there, I'm going to get 4 minus 2, so I'm good. So this limit should simply equal 3 times 2 cubed plus 2 squared minus 6 over 2 squared minus 2. Do the arithmetic. So this is going to be 3 times 8 plus 4 minus 6 over 4 minus 2, which is 24 plus 4 minus 6 over 2. And that's 28 minus 6 is 22 over 2, which is 11. Okay, so anytime we have a polynomial function, we can find the limit by simply plugging in the value. And if we have a rational function whose denominator is not equal to 0, we can find the limit by plugging in the value. All right, so what if there is a 0 in the denominator? Well, that depends. If there's a 0 in the denominator and the numerator is not equal to 0, so if I have some constant divided by 0, then this is going to actually either increase or decrease without bound. And that would mean that the limit does not exist. Okay, for some, if c is not equal to 0. Okay, but if c is equal to 0, so if I have something of the form 0 over 0, then we may have a limit. And so we're going to talk about some techniques to deal with. This is called an indeterminate form, and we're going to talk about some techniques to deal with that indeterminate form. Okay, so in the first case here, for example, if I went to plug in this limit, because I say, oh, it's a rational function, let me just plug it in, but I look and I see that my denominator is actually going to be 4 minus 4, which is 0. Okay, so now I have a 0 in my denominator. So if my numerator is not 0, then I can say it doesn't exist. But let's check the numerator. So if I plug it in the numerator, I'm going to get 4 minus, I'm sorry, I'm going to get 4 minus plus 2 minus 6. Sorry about that hesitating there. But 4 plus 2 minus 6 is also equal to 0, so I actually do have this indeterminate form. Okay? So one way to deal with that with rational expressions is to simply see if it can factor and reduce. So I'm going to rewrite this limit. and I'm going to factor the numerator. Okay, so x times x for x squared. 3 times 2 will get me 6. And then if I have a positive 3 and a negative 2, I'll get a positive 1 for my coefficient here and a negative 6 there. In the denominator, I can simply factor out the x. Okay? And I can see that we have a common factor, numerator and denominator, which is why we're getting 0 over 0. Okay? And so I can cancel these out, and the limit of this function should also equal the limit of this function. Okay? And now this function doesn't have a 0 in the denominator anymore, because as x approaches 2, the denominator is 2. So now we have a rational function without a 0 in the denominator that we can evaluate by simply plugging in the value that we're taking the limit at. And so we get that this limit is 5 over 2. Okay? So if we have a rational function, if the denominator is 0 and the numerator is not, then the limit will not exist. It increases or decreases without bound. But if we have a rational function, the denominator is 0 and the numerator is also 0, then the limit is probably going to exist. And one technique for finding that is to factor and see if I can cancel out common factors. All right. Another technique for that, so you see here, if we plug in, we're going to get 2 in the 2 minus 2, or 0 in the denominator. If I plug here, I'm going to get the square root of 4, which is 2 minus 2, so I also have that 0 over 0 form. But we don't have nice polynomials here that are going to factor for us, so we're going to have to try some other trick. And that other trick is something that you learned in pre-calculus. So we have a 0 over 0, and that is called rationalizing. Now, in pre-calc or college algebra or one of those courses, we always had you rationalize the denominator, but in this case, we're actually going to rationalize the numerator. And when you have two terms to rationalize, you're going to multiply by the conjugate. So I'm going to multiply by the square root of x plus 2, which is the conjugate, square root of x plus 2 plus 2, which is the conjugate of the square root of x plus 2 minus 2. So I'm going to do that to both the numerator and denominator because I don't want to change anything. So I want equivalent expressions here. And when we do that, though, remember that when you multiply conjugates, just in general, if you have a plus b times a minus b, then your middle term cancels out and you simply get a squared minus b squared. So that would happen here in the numerator. So I'm going to end up with the limit as x approaches 2. And so my a squared will be x plus 2 minus my b squared will be 4. And in the denominator here, I'm just going to have this mess of stuff there. Okay? But we can see some things happening, because if I take the limit now as x approaches 2, I combine like terms in the numerator, I'm going to get x minus 2 over x minus 2 times the square root of x plus 2 plus 2. And then we can see that these factors of x minus 2 in the numerator are going to cancel. And so I am going to get the limit as x approaches 2 of 1 over the square root of x plus 2 plus 2. Okay? And so now if I plug my 2 in, I am not going to get a 0 in the denominator. So I can evaluate this limit by go ahead and plugging the 2 in. Which is going to give me 1 over the square root of 4 plus 2 which gives me 1 over 2 plus 2, which is 4. And so this limit actually exists and is equal to 1/4. So whenever we have radicals involved and we have that 0 over 0 form, think of rationalizing, multiplying by the conjugate. Okay. The sandwich theorem, or squeeze theorem as I like to call it, is a nice little theorem to help us find limits. So if we know that two functions, g of x and h of x, and then we know their limits, okay, so we know the limit of g of x and the limit of h of x as x approaches some value c, and if f of x is between these two functions, then f of x has to have the same limit. Okay, so it's squeezing them between these two functions. So the idea here is, if I have, so this is the picture. So if I know that h is here and f is here, the orange color, and I mean g, and f is between these two, then as I'm approaching c, if both g and h approach this value L, then since f is between them, it forces f to approach that same value. Okay? So in this example here, it says find the limit of, as x approaches 0, of u of x, which is the function pictured in blue below. So basically we see that u of x is squeezed between 1 plus x squared over 2 and 1 minus x squared over 4. So if I find the limit of 1 plus x squared over 2, then the limit of u of x, and we're looking at as x approaches 0 here, should be squeezed between these two limits, by the squeeze theorem. And so these limits can be calculated, because if x is equal to 0, this limit on this side is 1. And the limit also on this side, if x is approaching 0, this limit is also 1. And so that means that the limit as x approaches 0 of u of x must also be 1. And that is using the squeeze theorem.